26,000 light-years from where you're sitting right now, at the exact center of our galaxy, there is a hole in space itself. Not a hole like a cave or a gap or an empty room, a hole in the fabric of reality, a place where gravity has folded space so tightly that light itself cannot climb back out. Every star you have ever looked up and seen, every planet, every comet, everything in the Milky Way is slowly circling this one point, the same way water circles a drain. We call it Sagittarius A star, and for most of human history, we didn't know it was there. For thousands of years, people looked up at the thick, bright band of stars stretching across the night sky, the Milky Way, and had no idea that behind that glowing river of light sat something 4 million times heavier than our Sun, packed into a region smaller than the orbit of Mercury. Here's what makes this different from every other black hole documentary you may have seen. This isn't some black hole in a distant galaxy billions of light-years away, understood only through abstract equations. This is the black hole that our Sun, our planet, and every version of here you have ever known is orbiting right now, once every roughly 230 million years. We have never taken a single photograph of it directly. We can't. Nothing can. But in 2022, a team of scientists did something that should not have been possible with our current technology. They produced an image of its shadow. Not a photo of it, but a picture of the exact boundary where light disappears. So what is actually sitting at the center of our galaxy? How do you even find something that, by definition, emits no light? And what does its presence tell us about the fate of everything orbiting it, including us? Stay with this one, because by the end, the center of our own galaxy will feel a lot less abstract and a lot stranger than you probably expect. To understand how astronomers found something invisible, you have to go back to a time when the center of our galaxy wasn't even visible at all. The core of the Milky Way sits behind thick clouds of gas and dust, tens of thousands of light-years thick. Ordinary visible light, the kind our eyes use, is almost completely blocked by that dust before it ever reaches Earth. For most of the history of astronomy, the galactic center was simply a bright smudge behind a curtain nobody could pull back. That changed in the 20th century, once astronomers realized that other kinds of light could get through where visible light couldn't. Radio waves and infrared light pass through dust far more easily. Starting in the 1930s and accelerating through the following decades, radio telescopes began picking up something strange coming from the constellation Sagittarius. A steady, compact source of radio emission sitting almost exactly where the mathematics said the center of our galaxy's rotation should be. In 1974, two astronomers, Bruce Ballack and Robert Brown, used a radio interferometer in West Virginia to zero in on that source with much finer precision than anyone had managed before. What they found was compact, intense, and almost point-like, far smaller than the fuzzy radio glow around it. They named it Sagittarius A, borrowing the star notation from atomic physics, where an asterisk marks something in an excited, unusual state. It was a fitting name. Nobody yet knew what it actually was. For the next 2 decades, Sagittarius A remained a serious puzzle. A radio source that intense, packed into that smaller region, ruled out ordinary explanations. It wasn't a cluster of stars. There were too few stars in that exact spot to produce that much radio emission from a region so small.
It wasn't an ordinary gas cloud either. Gas clouds don't stay that compact and that stable for so long. The leading suspicion, one that had been building in theoretical physics since the 1960s, was almost hard to say out loud. Maybe our galaxy, like some others astronomers had already started studying, had a massive black hole sitting at its center. But suspecting something and proving it are two different things. And proving an invisible object exists using nothing but the way it bends and pulls everything around it would take almost 30 more years of some of the most patient observational work in the history of astronomy.
If you can't see a black hole directly, there is only one way to prove it exists. Watch what it does to things you can see. Starting in the early 1990s, two separate research teams, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in the United States, set out to do exactly that. Their target wasn't Sagittarius A star, it was the stars orbiting impossibly close to it. Using some of the largest telescopes on Earth, the Very Large Telescope in Chile and the Keck Observatory in Hawaii, both teams began tracking a small cluster of stars swirling around the galactic center year after year, correcting for the blurring effect of our own atmosphere using a technique called adaptive optics. This let them see detail that should have been impossible from the ground. One star in particular became the key to the entire mystery. Astronomers call it S2. Every 16 years, S2 completes one full orbit around Sagittarius A star, an orbit so tight and so fast that at its closest approach, the star is moving at roughly 2.5% of the speed of light, whipping past the galactic center at a distance not much larger than our solar system. By carefully mapping S2's orbit, its shape, its speed, the way it curved through space, both teams could calculate exactly how much mass had to be sitting at the point everything was orbiting. The answer, confirmed independently by two competing teams using two different telescopes on two different continents, was almost unbelievable. Roughly 4 million times the mass of our Sun, compressed into a region smaller than our solar system, emitting barely any light at all. There was only one known object in physics that could satisfy every one of those conditions at once: a supermassive black hole. In 2020, Genzel and Ghez were jointly awarded the Nobel Prize in Physics for this discovery, sharing it with Roger Penrose, whose earlier theoretical work had shown that black holes weren't just a mathematical curiosity, but a natural, almost unavoidable prediction of Einstein's general relativity. Before we go further into what came next, if you want to see just how strange black holes get once you leave our own galaxy, the ones that tear stars apart, the ones bending light around themselves in ways that break intuition completely, we covered several of the most extreme examples in our video on the scariest places in the universe. It's linked right here, and it's a genuinely good companion piece to this one if black holes are a topic you're drawn to. For 30 years, the evidence for Sagittarius A star had been entirely indirect. The movement of stars, the mathematics of orbits, the radio emission of a compact source. Nobody had ever produced anything resembling an image. That changed in May 2022 when the Event Horizon Telescope collaboration, the same international team that had produced the first ever image of a black hole in the distant galaxy M87 3 years earlier, released the first image of Sagittarius A star itself. It wasn't a photograph in any conventional sense. No camera on Earth is powerful enough to resolve something that small at that distance. Instead, the team linked together radio telescopes spread across the entire planet, from Antarctica to Hawaii to Spain, timing their observations so precisely with atomic clocks that together they functioned as a single telescope roughly the size of Earth itself.
This technique is called very long baseline interferometry. What came back was a glowing, uneven ring of light surrounding a dark central shadow, the silhouette of the event horizon, outlined by superheated gas and light bent around the black hole by its own gravity. Oddly, imaging Sagittarius A star turned out to be harder than imaging the much larger black hole in M87, even though it's far closer to us. Because Sagittarius A star is so much smaller, the material swirling around it completes an orbit in minutes rather than days, meaning the image was shifting and changing while the data was still being collected. It took new computational techniques and years of processing just to freeze that motion into a single coherent picture. For the first time in human history, we had something that looked like a picture of the exact place where our galactic gravity becomes absolute.
You might expect that once you have an image, the mystery is solved. In this case, the image only opened up new ones. The first puzzle is how quiet Sagittarius A star actually is. Supermassive black holes in many other galaxies are ferociously active, pulling in enormous amounts of gas and dust, heating it to extreme temperatures and blasting out some of the brightest radiation in the universe, what astronomers call an active galactic nucleus. Sagittarius A star, by comparison, is almost embarrassingly faint for something 4 million solar masses in size. It appears to be feeding on very little material at all, and nobody has a complete explanation for why our galaxy's central black hole is so much calmer than so many others. The second puzzle involves its flares. Every so often, sometimes daily, Sagittarius A star brightens suddenly in X-ray and infrared light, sometimes by factors of tens, before fading again within hours. The leading explanations involve small clumps of gas spiraling in and being consumed, or turbulent magnetic field lines near the event horizon snapping and reconnecting, releasing bursts of energy, similar to solar flares, but on a scale tied to a black hole instead of a star. But the exact mechanism and why the flares happen when they do is still an active area of research rather than a settled answer. The third puzzle involves its spin. General relativity predicts that a black hole isn't just defined by its mass, it can also rotate, dragging the fabric of space around it with it. Measuring exactly how fast Sagittarius A star spins and in what direction relative to the disk of our galaxy is one of the primary goals of the Event Horizon Telescope's ongoing work. A follow-up image released in 2024, this time capturing the polarization of light around Sagittarius A star, revealed magnetic field patterns strikingly similar to those seen around the much larger black hole in M87, suggesting that whatever physics governs black holes at this boundary may be more universal than expected, even though the two differ enormously in mass and environment. And then there's the deepest, oldest puzzle of all, one that Sagittarius A star shares with every black hole in the universe. What is actually happening past the point where light can no longer escape? General relativity predicts a singularity, a point of theoretically infinite density where the equations themselves break down. Most physicists suspect this isn't literally true, and that it's a signal that general relativity alone is incomplete at that scale, needing to be combined with quantum mechanics in a way physicists still haven't fully achieved. Nobody currently knows what that combined description would look like, or whether it's something we could ever observe directly, even in principle. We have an image, we have a mass,
We have an orbit precise enough to set a clock by, and we still, honestly, do not know what is happening at the very center of it all.
It's fair to ask why any of this matters beyond raw curiosity. The answer is that Sagittarius A star has quietly become one of the most valuable laboratories in physics, not because we built it, but because it's the closest supermassive black hole we will ever have access to. Consider gravity itself. The extreme environment around Sagittarius A star lets scientists test general relativity in conditions that are impossible to reproduce anywhere on Earth or anywhere else nearby. The orbit of star S2 has already confirmed two predictions that only show up in extreme gravity: a gravitational redshift, where light from the star is stretched as it climbs out of the black hole's gravity well, and a relativistic precession of its orbit, a more extreme version of the same effect that slightly shifts Mercury's orbit around our Sun, first explained by Einstein over a century ago. Every one of these tests so far has matched general relativity's predictions almost exactly, which is itself remarkable, and any mismatch, however small, could be the first hint of new physics. Consider galaxy formation next. Astronomers have discovered that nearly every large galaxy appears to host a supermassive black hole at its center, and that the mass of that black hole seems to be linked, in ways still being worked out, to the properties of the galaxy surrounding it. Understanding how Sagittarius A star formed, how it grew, and why it behaves the way it does today may help explain a much bigger question: whether galaxies and their central black holes grow together, shaping each other over cosmic time rather than evolving independently. Consider the technology this required. Turning a planet-sized array of independent radio telescopes into a single synchronized instrument precise enough to image something this small at this distance pushed forward atomic timekeeping, data processing, and international scientific collaboration in ways that extend beyond black hole research. The techniques developed for the Event Horizon Telescope are already influencing other fields of high-precision astronomy. And consider what comes next. Scientists are already working on a next generation of this technology, adding more telescopes, including ones in space, to sharpen these images further, and eventually to capture something no one has ever seen: video, rather than a single still image, of gas swirling directly around the edge of a black hole's shadow, close enough to watch the process of feeding and flaring happen in near real time. We are quite literally at the earliest stage of a new kind of astronomy, one built around observing gravity at its absolute limit, using our own galaxy's black hole as the nearest possible test case. So the next clear night, if you can get somewhere dark enough to see the thick band of the Milky Way stretching overhead, look toward Sagittarius, low on the horizon depending on your latitude and the season. You won't see anything unusual, no glow, no distortion, nothing to mark it apart from the rest of the sky. And that's the point. 26,000 light-years away, hidden behind a wall of dust our eyes were never built to see through, sits an object 4 million times heavier than our Sun, quietly anchoring the orbit of everything in our galaxy, including the star we orbit and the planet you're standing on. We found it not by seeing it, but by watching a single star complete a 16-year lap around something invisible and doing the math. We photographed it not with light it gave off, but with the shadow it cast on everything glowing around it. And after all of that, the decades of tracking, the Nobel Prize, the planet-sized telescope built out of a dozen smaller ones, we still don't fully know what's happening at the point where its gravity becomes complete. Maybe one day a more complete theory of gravity will finally explain what sits at its center.
Or maybe that boundary, the one light itself cannot cross, is simply where our current physics runs out of road and something entirely new has to begin. Either way, the next time you look up at the Milky Way, you'll know that everything you're looking at, every star in that pale band of light, is slowly circling something we only recently learned how to prove was there at all. If this is the kind of mystery that pulls you in, this channel exists for exactly this: real, evidence-based deep dives into the biggest open questions in physics and the cosmos, without the exaggeration. Subscribe and turn on notifications so you don't miss the next one. If you're new here, go back and watch our video on the scariest places in the universe next. It's the natural next stop after this one, and it'll take you even further into what black holes are capable of. Drop a comment and let us know, if Sagittarius A went silent tomorrow and stopped anchoring our galaxy's orbit, what do you think would actually happen to the Milky Way? We read every comment, and the best ones often shape what we cover next. Thanks for watching. We'll see you in the next one.